Linear transformations, also called linear mappings, are actions which manipulate or transform a given vector. A linear transformation can rotate, even by a certain angle, stretch, shrink, and scale a vector, or it can place a vector on a desired axis, reflect it across an axis or any particular line, or move it to a higher or lower dimension. While linear transformations don't seem to represent them immediately, they can be thought of as functions. The manipulation of a vector or set of vectors can be considered a linear transformation only if it satisfies this statement. We want a given manipulation to be a linear transformation because if it is, it can be useful for all vectors in a given set, which is to say, vectors of a certain type or form, and it can give us useful information and then be used as a tool elsewhere. If the definition only holds for a single vector, it is not of much use to us. You can think about it like an equation and whether that equation can be considered a function, aka if it passes the vertical line test. If it does pass the vertical line test, it becomes very handy and we can do all kinds of things with it. Linear transformations themselves have several characteristics unique to them, such as kernels, codomains, images, and ranges, but I'll save those for a later video. Technically speaking, this definition merely displays the, quote, preservation of addition and scalar multiplication. All it says is if we have two vectors, multiply each by a different number, and add them together, and then apply the transformation, it would give us the same answer as applying the transformation to the vectors separately, multiplying them by a number, and then adding them together. Since alpha and beta represent any and all scalar values, and v1 and v2 represent any two vectors of a certain type, proving a linear transformation holds for generic vectors means it holds for all vectors of that form or type. Sometimes higher dimension transformations are hard or impossible to graph or imagine. Luckily, there's no need to do so long as it can be tested against the definition. So, in this example, we have a linear transformation which takes a two-dimensional vector and transforms it into another two-dimensional vector. So we have our vector, and the result after pushing it through our linear transformation makes its x2 value negative. And this reflects a reflection across the x1 axis, which is just your x-axis for any other math class. So we'll have our generic vector, we'll name it u, and we'll say that its components are x1 and x2. And in this example, I have multiplication and addition proven separately. In my other example, I'll have those combined into a single statement. They can be easier or harder depending on what you're working with. The only real way to figure that out is just with practice. So for multiplication, we'll say that alpha is a real number, and we'll go ahead and multiply our vector u by alpha before applying the linear transformation to it, which gives us this, and which gives our pre-transformed vector alpha x1 and alpha x2. And once we apply the transformation to it, we now have alpha x1 and negative alpha x2. So at that point, we can pull our alpha back out and say that this statement here is the same as saying alpha times the vector x1 negative x2, which is the same thing as saying alpha times the linear transformation of u. So in that case, those two things are equivalent. It means we have retained the property of scalar multiplication. For addition, we have now two arbitrary vectors. We have our generic vector u, which is comprised of x1 and x2, and then we also have v, which is comprised of y1 and y2. So we'll go ahead and add them together before we apply the transformation to it, which gives us just x1 plus y1 and then y2 plus x2. And once we apply the transformation to it, that gives us a result of x1 plus y1 and then negative x2 minus y2. And we can separate those back into x1 and negative x2 plus y1 and negative y2. In which case we can further simplify it and say that all of that is equivalent to the transformation of u plus the transformation of v. And since addition holds, this is a true linear transformation. So here's our second example for a linear transformation. In this case, we are taking a vector from R3 to R2. So we're taking a three-dimensional vector and making it a two-dimensional vector. So we have our generic vector in R3, so that's x1, x2, and x3. And then once we apply the linear transformation to it, we're basically just going to drop the x1, and then we'll just have x2 and x3. So again, we'll define our generic arbitrary scalar multiplier, so that's alpha and beta in this case. We'll state that they are within the real numbers. We'll give u generic components, so x1, x2, and x3. And we have v again, and that'll be comprised of y1, y2, and y3. So this is what we have when we combine our addition with our scalar multiplication. So we will multiply the vectors and then add them together before we apply the linear transformation. So here, that's the equivalent. So we're saying u times alpha plus v times beta, and that gives us the linear transformation of alpha applied to all the components of u plus beta times all the components of y. And we're going to further combine that with addition. So now we have alpha x1 plus beta y1, etc., etc. And after this, at which point we will apply the linear transformation. And once we apply it, it gives us this. Like we said earlier, all we did is drop the x1 term. So now we have alpha x2 plus beta y2 and alpha x3 plus beta y3. And we can pull out the alpha and beta, which gives us alpha times x2 and x3 plus beta times y2 and y3. Then we can further simplify it and say that this is equivalent to alpha times the linear transformation of u, which is true because we have x2 and x3. We started with x1, x2, and x3. And we can say the same thing for beta times the linear transformation of v. So we have proven it in the same expression for both scalar multiplication and addition. In summary, a linear transformation is essentially a function which can be applied to vectors of a certain type. It will predictably scale, stretch, and rotate vectors, among other actions. As long as the definition holds for the generic form of a vector and for generic scalar multipliers, it will hold for every vector of that type. I hope this was helpful to you in some form. Thank you for watching. We'll see you next time.